Welcome everyone, and thank you for joining us today for our third of 3 one-hour webinars on quality control in the Serology Laboratory. My name is Amin, and I'm the Territory Manager for the Midlands here at AB Scientific. For those of you who don't know us, we were formed in 2014 and supply products to the UK and Ireland from our offices in London and Dublin. Our Clinical Solutions division comprises of a portfolio of products around third-party quality control, assay verification, verification data processing, and interpretation covering all clinical disciplines across pathology. I'm delighted to welcome Joe Vincini from the NRL, who will be discussing quality control in the Serology Laboratory, expanding the boundaries, QConnect limits, and other methods to identify variation. Before we begin, I would just like to run through some housekeeping. This webinar is being recorded and will be available to watch again from our website in the coming days. For the benefit of viewers, everyone's microphone has been muted. If you wish to ask a question, then please feel free to pop it into the chat box at any time. The chat can be accessed from the speech bubble at the top of your screen or bottom if viewing through a browser. If you're on your phone, then honestly, I don't know where it is, but I'm sure you guys will be able to figure it out. To improve your experience during the webinar, once the presentations has started, please click the focus button from the menu and that will make the presentation full screen on your device. Myself and my colleague Aaron will be managing the chat, and at the end of the presentation we will answer as many questions as possible. If we don't manage to get through all of them, then we will publish them on our website alongside the recording of this webinar, so please look out for an email in the next coming days for a link. If you would like to ask any questions, then please privately email events@abscientific.com and we will get back to you. So without further ado, I will now hand over to Joe, who will now present quality control in the Serology Laboratory and how it improves quality of testing. Over to you, Joe.
Thanks for the introduction, Armin, and thanks once again to AB Scientific for allowing me the opportunity, or for allowing NRL the opportunity to participate in this webinar series, and the third of the series and the final, just in time for Easter and to break. So I see that people are still coming along, so hopefully they won't miss too much, but there's a recording anyways, and you can get the recording from AB Scientific typically the day after the presentation has ended. Once again, and whilst people are joining, I'm going to do a couple of slides within the presentation where we're using Slido to complete some multiple choice questions, and I'll just give you the opportunity now, whilst we're waiting for a few more people to join the call, to use your smartphone and scan this, or you can use the link there at the slido.com website and use that code to gain access to the presentation questions. There's a couple in there, and it would be good to gauge, if people could participate in that, to gauge, some of the key thinking that people have around the way QC is used in particular. You will get that QR code and link as well in the slides that I'll show you, so you'll get another opportunity. Hopefully you've had a chance to scan that by now, so let's see how we go. So I want to start off once again by bringing up a slide that I showed on the second of the three presentations, and that is really to bring back to mind what it is that we're trying to achieve with quality control, and that is the detection of defects. And this really is a manufacturing term that has been borrowed in laboratory medicine. So just keeping in mind that what we're trying to do is detect defects, and how we do that in a laboratory is a little bit more specific around identifying defects in the laboratory setting than it is in manufacturing. So you'll recall that in the second webinar I introduced this case here, and so this was a case looking at two assays on the Abbott Architect, and so what I presented that day was that even though these look like they're pretty identical, they both demonstrate lot variation. The different colors on these two Levy Jennings charts show different reagent lots. And what we're trying to show here is that, yes, there's something going on in one of these, possibly. What is it? And so last time I said, yes, there's something going on, and I promised that I would talk about it today, and I will use this example in the whole context of this talk. But without context, it is very difficult to know what is going on. And using traditional methods, you probably would disregard that something was going on in this assay in the first place. So if we really break this down, I want to look at some of the data that's going on behind these assays. So if we were to use mean and standard deviation for all these different reagent lots. So with the HIV combo assay, we had 4 different reagent lots in use. And with the anti-HCV, we had 5 different reagents in use. So the key part I want to show you here is what the means look like for the 4 different reagent lots, the number of data that were used at the time, the standard deviation, but really just the mean and the 3 SD, both positive and negative. So you can see here in the red, the positive and negative 3 SD, and in the whites, the mean for both assays. But it's very difficult to see what tables are telling you. So I'll show you what these look like when broken down. So applying mean and 3 standard deviation for each lot, you can see that they shift around. So look, keeping that in mind as to how these data would be represented by using traditional methods, yes, you would find that immediately moving on to a new reagent lot, you would find that data would be rejected or be outside of that lower S3SD or upper 3SD. So you can clearly see that that is going on. And yes, also we're looking at the anti-HCV, you still see the same thing going on with this assay. So keeping those 2 examples in mind, without context, these cases seem identical, and laboratories would likely take a number of directions in how to address this lot variation. So I now bring you to your first Slido, if possible. If you haven't set up your phone, here's the QR code once again, and there's the website that you can link up to. And if you want to follow that, if you can start putting in your answers, I know that it's a chore, but you know it'd be good to see what's going on there. So, and I'll give you some time to do that, because I know it takes a bit of time bit of lag in getting the information across all the way from Europe to Australia. So obviously this is a live poll, so you can see people start to enter it in, and don't feel the pressured into following the same answers as everyone else does. I guarantee you the answer isn't as obvious as you think it is. And as expected, you know, the majority of answers will be around, yes, we would recalculate the mean and standard deviation. And you know, in my mind, and I don't talk about this a lot in the whole presentation, but when recalculating a mean and standard deviation, what does that mean to the results that you've already validated and accepted in the past using a different calculation of mean and standard deviation? Does that really change whether those results in the past should be accepted or not? I mean, it's an interesting concept and it's probably worth another discussion. But really just going on from that, and it's good to see that not many people ignore the result and make an educated guess, because I think you wouldn't be at fault to actually do that, to be honest. But in actual fact, there's probably no correct answer to this, in my opinion, and that is because there's no context. So recalculating, I think, is a very difficult thing to do in qualitative testing, and I don't really believe that it gives you the answers you want. And a lot of this is because lot variation is known to be a large source of variation in qualitative testing, and it is often ignored or limits are adjusted to accept those results. And that's what we mean by recalculating the ranges so that we could accept results. And often laboratories retest and retest and retest just to get a result in there to avoid that whole situation. And so laboratories end up having 2 paths that they take. One is that they see everything as a problem lot everywhere, and so they spend a lot of time and resources investigating all instances. So they're overreacting to every situation that they have with regards to lot variation, or they spend their time underreacting, which is they know that lot variation is a major source of variation, but don't see it as a problem, and so they often just ignore it and carry on without actually doing anything about it. Now, going back to this example, some commentators would argue that calculating mean and standard deviation from a very small data set isn't really representative. And so what they argue is that the data set isn't large enough to set a range, and so you should really extend that out. So let's say if we used more reagent lots to extend that out. Well, if we look at what happens if you include the first 3 reagent lots, you immediately can see that the first the first 3 lots were used, if they're used to calculate mean and standard deviation, that's what it would look like. So you do start to introduce more of a spread so you can be more inclusive in those data. But the minute, and invariably it happens sooner or later, a reagent lot will come along that will be outside. And that is because in this particular case, it happened to be the next production lot that was introduced, but it could be further down the track. That is because small data sets to calculate ranges don't often represent what is going on in the future, and it's just too small and doesn't really look at the bigger picture of what is going on with an assay QC relationship. So what is it that we really wish to identify when using QC? What is it that we really want to do? And here's your next question. So this will be your last challenge, so hopefully it hasn't been too much of a chore, but it really brings home some of the thinking that you need to do when looking at QC and assay combinations and looking at testing. Good to see a good spread of results. I once again have to remind you that just because one answer gets a lot of votes doesn't necessarily mean it's the right one. So not that there's a right one in this case, but there is a favoured one, in my opinion. Okay, so I think we get the picture here that the 2 areas that most laboratories would see is, yeah, I want to identify variation, but there's also the idea that we have to validate results. And that is a common area in QC. So if we had ranges that were of context, and I bring up QConnect limits for the first time, but I will start to explain that a little bit later. So if we had ranges that have context, so here we have the QConnect limits as we've calculated them for this assay QC combination, and that's using extensive historical data to do that. So with context, the lot variation here that we're seeing in the HIV combo assay has no bearing on the outcome. We see lot variation a lot, but historically we've seen that before. And so we expect that even though we're getting lot variation, it's unlikely to be impacting on clinical sensitivity. In most cases, it won't be. And in this particular example where we were looking at the HCV, then with context, the lot variation does have a bearing on the outcome because historically that the data fall within that range. And so when we start to see things outside of that, that's where we're starting to see areas of out of character or things that we haven't seen before. So it's meaningful QC that gives context with qualitative data. And so expanding on this concept of meaningful QC. So many of us see QC as a checkbox exercise. The standard requires us to do QC, so we run QC. Or this is what our assessors want to see, so I'm running a QC program. But I don't see any value in it. We're just, checking the boxes. So I've introduced the standard, so let's look at the standard. So ISO 15189, which is medical testing standard. This is pretty much all it has on quality control in that 40-page document. And so it's not a lot in there, but it's pretty important what's in there. There's not many requirements, but those requirements are pretty straightforward in trying to follow. So I think this line here, the laboratory in 5.6.2.3, the laboratory shall have a procedure to prevent the release of patient results in the event of quality control failure. For qualitative assays such as in serology, I think the kit controls fulfill most of these requirements. And so is it really speaking about an externally provided QC or an internal quality control for the release of results? I don't think that was the intention, but that's an interpretation of that. So, but what the kit controls can't do is it can't help you with understanding variation of concern because they aren't independent. They are built to do one thing and one thing only, and that is to validate the run. So your validation of results is done by the kit control in serology. In most cases, that is where the instructions for use actually indicate that the kit controls provided must be used for the validation of run. Also, it's interesting here in this red box here where it says when the quality control rules are violated and indicate the examination results are likely to contain clinically significant errors. What rules are they referring to? What quality controls? It doesn't tell you any rules in there. It certainly can't be referring to Westguard because it doesn't mention Westguard in there at all. So really what it's referring to by rules is what you have set down in this area here, this 5.6.2.1. The laboratory shall design quality control procedures that verify the attainment of the intended quality of results. So it's whatever procedure you put in place to do that. And there's no statement of what that procedure should be. So really it's up to you to define what that is. The standard also asks for more information than just acceptance of valid results. It's asking for you to monitor data, to record data, to detect trends, to indicate problems in the examination system, and to put in effects that have preventative actions as well. What's interesting is note 1 and 2 as well. So note 1 states that control material should be chosen at or near the clinical decision point. But in serological testing, in most assays in serology don't have a clinical decision point. There's an assay decision point. We went through this in the webinar too, and looking at what it is that is actually being referred to as this clinical decision point. So having a QC that is very close to the cutoff doesn't necessarily mean that you're challenging the decision point. You're challenging where the assay decides that something is positive or negative. But we already know that assays at that point don't necessarily behave the same way that they do when challenged with a true low positive, as in a seroconversion sample. It also mentions in note 2 that a third-party QC would be used instead of or in addition to kit controls. This is clearly not written with serology or qualitative testing in mind. So it highlights that the thinking behind these statements were not likely for qualitative testing. This is for quantitative testing. And in particular in chemistry, where many assays aren't provided with a control, or if they are, you can substitute them out with a third-party QC. So if the instructions for use for a serology test tell you that you need to use the kit controls, you have to use the kit controls. If it doesn't state that, then you possibly could change them out, but you need to have a good validation procedure to ensure that what you're substituting are actually suitable for that procedure. So going back to this checkbox exercise and meaningful QC, without context, QC is meaningless. So how do we make QC data more meaningful? Let's go back to webinar 2, and I introduced that graph of what do the numbers mean? Do the numbers really mean anything? And I want to bring back this point about peaks move around a lot. And so what we see with lot variation in serology tests is that the peak of positive results do move around. As we see lot variation, what we're really seeing is this, where the results move around. And traditional methods do not deal with lot variation very well. They don't know how to deal with it because they do move around. And we know that you change any component of the assay in the manufacture, then the performance changes. So it doesn't know how to deal with it. So we do have to recalculate the mean and standard deviation. But it doesn't really tell you what's going on in the bigger picture. So the bigger question really should be, is all lot variation a problem? Or is it only some of them? And how do you know which ones? What happens when we look at how a well-characterized QC is used on a validated assay? So in the beginning, there would be no guidance of what the range should be. You don't have any range. So you'd have to start testing and generating data. Now, laboratories need to decide on what QC range they should use. Laboratory staff rely on published guidelines for that direction. There are some out there. There's several. There's one that you're well familiar with, which is your own national standard method, which advocates that in the past used to direct that you had to use 20 results, calculate a mean and standard deviation, and then apply Westguard rules. They're sort of coming back on that now. I don't think that is, in this modern world, a suitable method to use for QCing serology results. It may be suitable for chemistry, but I think they're even moving away from that in chemistry as well, and looking at other methods like Six Sigma and other ways of looking at statistical methods to look at data. Now, the CSLI methods, the CSLI guideline says that you can use 20 plus, which I say 20 plus because what it actually says is use 20 results, and we acknowledge that that is not enough and generally continue until you're comfortable with it. So it could be 100, could be 1,000, whatever it is, and then apply some statistical method to identify whether there's something out of character or not. The other one that we generally look at and we've published on this in 2018, we looked at all three of these methods in comparison to QConnect limits, is the the German guidelines used in Germany and possibly other countries. And this is a mathematical algorithm that looks at bias and all other areas as well. But in qualitative data, it's acknowledged that bias, you can't assume bias. So there's no bias. So when taking bias out of that algorithm, what we're looking at is mean plus 3 SD out of 15 results, not 20 results. So it's a smaller data set, but a wider range rather than 1, 2, and 3 standard deviations. And then we also have QConnect limits. We've published on this, it's out there, and I'll talk a little bit about that now. But what we use is historical data. We don't set what number those results should be, or that those data used to calculate the range. And what we would expect and what you assume is that that range just keeps getting wider and wider and wider. There's a number of things that limit that, but I'll get to that. So it is a published methodology. It uses historical data instead of a small data set to calculate what that range should be. So that could be thousands of QC results rather than that very small data set of 20 or up to 100 results. It is a robust scientific approach that has been peer reviewed, and we believe it is superior to Westgard rules and the traditional QC monitoring processes for serology. So it uses optimized QCs for each assay and minimal lot-to-lot variation. So these are the keys to it. And to do that, you require access to consistent stock material to manufacture. Now, the assay QC combination have specific calculations. So anything changes in the QC, anything changes in the assay, all bets are off and you have to start again. But what that also means is that there's one QC and one assay. There's no alternative. There's no other possible QC. Oh, I want to use this other assay with my QC, so can I use this new different QC because I use my HIV and my CMV at the same time, but CMV is not in that QC. So can I change it? No, there isn't. There's only one alternative, unfortunately. And what we're really looking at is that the methodology calculates variance of results, so between and within QC lot manufacturers. So when looking at meaningful QC, traditional methods don't deal with that lot variation very well. The bigger picture is around lot variation of the problem. So in the beginning, we said that there'd be no guidance on what that range should be. So how does this play out in real time? What does it look like when you start out? And I need to emphasize that QConnect limits, unfortunately, the way we do it, because it looks at the variance between lots, so the intra-lot variation, you really need 2 QC lots. So we needed an alternative to look at. So what we do is we do apply mean and 3 standard deviation at the very start, and then that expands until we get the second QC lot out. So this is what it would look like. And we've used this example quite a lot, this Architect anti-HCV. So I'm going to use this again for this series of examples. So we've got Optitrol Blue is the only QC we would offer for this assay. And it was this QC type was first released in February 2017. So this is what happened at the very beginning. So we had no previous data. One laboratory starts testing, and this is what you get. So you've got one QC lot from February 2017, one reagent lot in use, one user, 3 data points. So that's what we're looking at here. So what happens is that we also looked around and we said, okay, but what we really want to do is have an inclusive peer group that introduces different assays, different instruments from different laboratories, different reagent lots that they're using, the operators that are using the instruments, the conditions in the laboratories, the calibrators they're using. All that adds to the picture of variation. And that is important in setting meaningful QC statistics around the assay use. So it incorporates all sources of variation. So what we're starting to build is, at the same time, we looked at who else was using it. There were at that time 2 reagent lots in use, 2 users using it, and 5 data points. So in the early stages, very small amounts of data, and we can't really calculate any meaningful statistics around 5 data points. So what we found that after 1 month, the picture started to build around this. So we had 20 results from 4 reagent lots at the end of March and 3 users using the system. So after 1 month, we had enough data to begin calculating some statistics. So this is what it looks like, applying mean and standard deviation, so mean and 3 SD around these results, until we could build enough data to calculate QConnect limits. So we can see here that the upper and lower limits are around 3.1 and 2.5, so fairly narrow, and that's expected because it's a very small data set. But as the picture starts to build, we've got 2 months worth of data here. And we're seeing 6 reagent lots, 7 users, probably multiple instruments in use, and 87 data points. So after 2 months, that starts to build, and the range is starting to spread out. We're starting to get a fairly consistent mean, but the SD is starting to build. And we're starting to look at 3 months worth of data, and we get the introduction of the first outlier here. And so what we're seeing here is that there's a set of results used by one laboratory that are higher than everyone else. And that has an impact on this because we've got a small data set, anything outside is going to impact the mean and standard deviation, as you would expect. So this is already impacting the SD, and so we're getting a much larger range. So it's going from 1.8 to 4 now. And we've got 10 reagent lots, 15 users, and 264 results in the first 3 months. But as that goes out to 5 months, this laboratory has introduced other results which are normal, but we've got a much heavier weight of data here. This SD is tightening up, the range is reducing again, but we're seeing 30 different reagent lots used in this data set here with 18 users and over 1,200 results. So that's really starting to tighten up the range and really needs to, well, probably has already triggered investigation into what's going on with that one. But at that point in time, we would probably have already initiated that investigation. And so what was going on out of interest in this investigation, the data here we see are sorted by laboratory at the bottom, but we've got the specific reagent lot only that was causing this problem. And you can see that this laboratory was an outlier, that everyone else using that reagent lot was inside. And so whether they could then be requested to look into whether they had different calibrators to everyone else, or whether they had their reagent lot damaged during transport, or whether they were reporting data from the correct QC or not. It's highly likely that because this was early days, it could potentially be that they were using an earlier QC and were submitting those data into the wrong assay peer group. We don't know because this was 5 years ago, so we didn't really. I don't recall having that discussion with this laboratory, but they did go back to normal after that investigation. So this was definitely an outsider from a single reagent lot. And all other data are as expected for everyone else. So what we found was that after the first year of data, this is quite a heavy data set now, quite a lot of users. We've got 51 reagent lots in use, 35 users, and about 7,500 data points at this point in time. And that's all contributing to a fairly consistent upper and lower limit based on mean and standard deviation only. So it's still not QConnect limits because we still don't have enough data. And at this point in time, at the end of the first year, we were still using the same QC lot. So we weren't really able to calculate QConnect limits the way we would like to. So there's still only the one and no QConnect limits yet. So at the end of the second year, so at the end of December 2018, the range had settled even more. So it's very close to what it was before at the end of the first year. But at that point in time, we had actually introduced 2 more reagent lots, QC lots, sorry. So we've got 75 kits in use, 75 reagent lots in use, 57 users, and about 20,000 data points. So we had about 4,000 data points submitted for the 2 new QC lots that were circulating around for this assay QC combination. And so what we then started to see was the range was fairly settled, but we could calculate QConnect limits. So now we've got in orange what the QConnect limits would look like, and that's where they would be in the red. So that's introducing intra and inter QC lot variance into the calculation. Pardon my typo there. And so that allows for the limits to be applied. So you can see the difference in the limits there. So the limits are 2.1 to 3.6, and regardless of what the mean and SD was, that barely changes, even though we've introduced more QC lots, even though we've introduced more data into the system, even though we know that there were specific errors around that after this point in time, which was at the end of 2018, we know that doesn't really impact what the range should look like. So here we have 3 years worth of data, and we know that there is a known issue around some of these data. So we've got 7 QC lots in use at this point in time. So you can see here, 124 reagent lots in use, 81 users, about 40,000 data points, and the QConnect limits remained unchanged. So we know that there was an issue around these data, and most of these, well, pretty much all of these low results were attributed to one specific issue that was going on with this assay at that point in time, around the early 2019s data. So this is what we had with regard, we've got until this point in time with QC lots. So we've got about 13 batches of Optitrol Blue manufactured. These are all the different reagent lots, and there were varying numbers of QC data that submitted to these. Some were only trial lots, some were much bigger, some are still in use now, and the data are still being gathered. So what we found here was the early days where we introduced mean and standard deviation. Those are the two limits that we would have applied, but this is the QConnect limits, and they've continued for every lot since then. And we can see the consistent means and that we're seeing across here. This is, interestingly, that assay is no longer in use now. We've moved on to the anti-HCV2 for the architect. And once again, the mean and standard deviation seems fairly consistent. And we can see here that the mean and SD for the first lot was applied because, as I said, anything changes, all bets are off. We have to start again. So we have to start again for that particular one. We gathered a few amounts of data, then we moved on to the next lot, and then we could calculate mean and standard deviation again. Sorry, the QConnect limits. But because we had quite a few production lots in circulation at the time, we could quickly gather what that QConnect limit would look like. So going to the original issue here, I highlighted that there was this issue earlier on, and I indicated in the peer group data that looks like there was something going on, and that's why we had a lot of data that were low. So meaningful QC would identify that there was lot variation of concern here. And so based on the variation being outside of historical performance, and by historical I mean 40,000 data points, then we know that this one is something that is outside of character, out of character. And so that would lead us to further investigation rather than run rejection. We would have to investigate whether it's significant and whether it's of clinical impact on the results. And so what we then looked at is other methods to investigate these. So one of those was a quick way of looking at these using some of the tools within EDCNet, which is to sort the data by peer group. So what we've got here is we're sorting the peer group data here are sorted by reagent lots. So here we have the reagent lots, all the different reagent lots. And these ones here have a lower mean than all the others with results that are going below. So these lines represent two standard deviations of all results reported for the particular assay, and the crossbar is the mean. And so we had a series of reagent lots that were affected during the manufacture process for this. They changed one of the components, one of the buffers in it, and that had an impact, a downstream impact on the performance of these assays. So the problem was identified and was rectified. We had a study that went on, we published on that study, worked on it with Abbott, and that showed, using the information that we gained from QC, we could then investigating it using EQA data and also seroconversion panels, true positives, true negatives, to try and come up with whether this was going to impact the clinical sensitivity of this assay. And what it found was that there was a very, very low probability that it would miss some of the very early seroconversion samples. It only missed like 2 out of a whole series of seroconversion panels, and it would only be in the order of maybe half a day of detection in a seroconversion to 2 days in a seroconversion panel. So why do we need an alternative approach for qualitative data? And that is because QC for traditional approaches using QC in traditional approach has a number of assumptions, and these assumptions are that it assumes that there's normal distribution of QC results. And so both webinar 2 and today, I've been able to demonstrate that there's no normal distribution of qualitative results, particularly when there's a positive and negative population. That data set used to establish the limits are representative of future results, and that patient and QC sample results change proportionally. That is, if my QC is moving up and down, it means that my patient result moves up and down. And that is not necessarily the case. You can test a QC and a patient sample side by side 20 times, and you'll find that sometimes it goes up and goes down, whereas the QC goes down and goes up at the same time. They may all both shift up, they may both shift down if you're lucky. And so these 3 statements, these assumptions are not true. And so if we look at the traditional approaches, the traditional way we would approach this is to look at a data set, any data set, take any data set. And I've shown you a few already, but this is another one using the Architect HOV combo data. And you take the first 30 results and calculate mean and standard deviation from that. And so here in this particular case, here's the 30 results showing what the mean of those is and the 2 standard deviations of those data are. Then you apply that to the future results. And we can clearly see that there's a lot of results. We have to recalculate, or we have to take a different approach to how we analyze these data when we know that there's nothing really going on with this assay. If we were to apply 3 standard deviations to that, all of these results outside will be rejections, and we'd have to do something about it. So more than likely we would get up until this point and we'd be starting to think about recalculating. But what does that mean for all the results that you've already validated in the past? And if the numbers truly represented something, as in an amount of material or an amount of antibody in an assay or in a patient sample, then are we validating something based on misconceptions of how we validate them in the past? If we were to apply meaningful QC, like meaningful statistic around it, such as something like QConnect limits, then we know that historically these variations in lots performance don't necessarily always mean that there's something going on. So what we really need to do is take the value of what is going on with QC. We need to value our data. And so QC is only meaningful when we do something about it. Now, the standard, I've come back to the standard. I introduced it before, so I'll come back to it. So it does state here that shall be reviewed regularly at regular intervals to identify trends and act. So that's what it says in this red box, to fix what's going on, not only fix what's going on at the moment, but also to put in preventative actions to prevent things from happening in the future. So I emphasize that you really need to record your data on time and do it regularly, and also to use the systems that compare peer group data, not just individual data. Using an Excel spreadsheet is great, but you don't know what's going on with others. You may not know if you're in isolation or if something's happening to yourself, and particularly seeing something going wrong and then reporting it and to an assay manufacturer. They may say, well, we haven't had this report before, because potentially that is the truth, that there's no one has reported any of those instances, because most people may be in isolation and not understand what's going on. So it is really good to report your results into a peer group system so that you can monitor all the real-time performance of assays and whether there is something going on at the time. So we don't sit still. We don't just sit on our work and say, oh, yeah, we've created QConnect limits. That's great. We're always looking at next steps. So we know that there are some areas that we need to cover, and I think random error is the main problem that I have with QC in general. This remains the most difficult area to explain, regardless of the QC method you use, whether it's a traditional approach or an alternative approach. And so by random error, I mean these spikes that you see. You see these all the time, these drops or spikes. And so without analyzing these, mostly what happens is you see a spike, you retest the next result or the next day, it goes back to normal. And you think, okay, let's forget about it. It was a random error, can't be explained, can't do anything about it. Most cases you can't explain. But in some areas, I think we need to have mechanisms that alarm. I think QConnect limits handle some of these really well, like in this particular drop here, where it's going from positive to negative. It's likely that you didn't add substrate, or the substrate or the conjugate wasn't added, and so the substrate doesn't change or something like that. Hard to do in an architect because it's a closed box system, but in a manual assay, you could explain it that way. But having a miss like that, probably it's likely that you didn't add the sample, or there wasn't enough sample and it didn't sample well. But you don't know. It's hard to understand what's going on with random error. So it could be data entry error, could be a legitimate performance issue, we don't know. And it's hard to investigate when data return to normal the next time you run it. It could be a case like in this little blue dot here, that's a data entry error, and it should have been this red reagent lot rather than this blue one. And that's a simple one to fix. But it's these shifting ones around here that are more difficult, especially when they're within QConnect limits and they don't really ring any alarm bells. So in this particular case, we're looking at other ways to investigate data. We've pretty much almost completed our study on percentage CV, and we think that would be a good way of supporting QConnect limits at the local level. So your data only, not others' data influence. So QConnect limits would remain the absolute limits for an assay QC combination. So anything outside that would be extremely out of character. But at least percentage CV will allow users to monitor individual reagent lot variation on a local scale. So knowing that particular reagent lots would it be expected to perform in a certain way. Using historical data, we can gather a lot of information on what the typical percentage CV is of a particular assay when using a QC on it. So what it would look like is something like that. And so then you could then trigger whether any results are outside the percentage CV expected, but it would only trigger your data, it wouldn't trigger everyone's data. So at least that way, those alarm bells would only be yours and yours alone. So that would be something that we'll be implementing in EDCNet very soon, I think. But we're just about to publish on that, so we'll probably release those data, those functions within EDCNet pretty soon. So I'd just like to wrap up with some conclusions in that us as scientists in any discipline, we rely on QC to make informed decisions on how our assays are performing. And we believe that QConnect Limits includes all sources of variation. So it gives us a really good picture of what's going on with our assay, rather than trying to look at specific areas of an assay, such as what the numbers mean. And the numbers don't always translate to whether there's something going on with an assay or not. Without context, it makes it difficult. QConnect Limits are more suited to qualitative data testing than traditional approaches. We talk about Westguard a little bit, but it's almost gone in clinical chemistry, and it certainly is being developed into other methodologies now. And mostly because it gives you too many or not enough messages in serology to identify whether there's real issues going on. And sorting out the wheat from the chaff is very difficult in that. Recalculating mean and standard deviation is not always possible and not practical. In many cases, if you're a large laboratory, if you're a donor screening laboratory, for example, you do a lot of testing on the same reagent lot, so you can gather a lot of data. But small laboratories tend to rotate through reagent lots fairly quickly and don't gather enough data to be able to calculate meaningful mean and standard deviation on that one reagent lot, and so they'd be all constantly recalculating their mean and standard deviation and not have enough data to get any meaningful stats around it. But what is clear is that we have need for better understanding of what QC data are telling us, because there's a lot of messages out there, and we really need to have a forum to get together and understand what it is that we're looking at. I think having a case study webinars would be a great way of looking at that. And I thank you for your time and listening.
Thank you, Joe. We did allocate some time at the end of this presentation to take any questions that might have come through in the chat box. I don't think we have received any questions in the chat box. Yeah, I think you've explained everything really good, maybe, Joe, and no questions have come through. But if anyone does have any questions, then please feel free to email us at events@abscientific.com, and we'll make sure to get those answered for you, and they'll be published online as well. So yeah, I guess if there aren't any questions, we can close the webinar. Thank you everyone for attending the third of 3 webinars on quality control in the Serology Laboratory. We hope you enjoyed today's presentation and found it useful. And thank you, Joe, for presenting and taking the time out to do this webinar for us. We really appreciate it. We will email a link to of the recording to everyone in the next couple of days, so please keep an eye out for that. And if anyone would like any further information on the NRL solutions, such as EDCNet software, then please feel free to email info@abscientific.com or visit us at abscientific.com, and we'll make sure to get that information sent across to you. Thank you again, everyone, for attending, and I hope everyone has a great day. Thank you and goodbye.